Okay, so here's an application problem of Newton's second law. This is these are commonly known as mass and pulley problems or many body problems. Many body just because there's more than one object. So here's two objects connected by a string being pulled by an applied force of 20 newtons. Now there's a couple of ways to solve this. One I'll call the system approach, and that works when it's a very simple problem. So here it's just two blocks and a frictionless surface. So what we do in this case is we treat the system as a single object, a single 5 kilogram object, and then just write a force equation. So on that 5 kilogram object, which is represented by this dashed line, the forces that act will be a weight force and a normal force. And those are just going to be balanced and cancel each other out. So the net unbalanced force is this 20 Newton force. So on the 5 kilogram, if we write net force is MA, the net unbalanced force is the 20 newtons. The mass is the mass of the system, 5 kilograms. And so we can solve for the acceleration by division. 20 over 5 is 4. Now, to look internal to the system, say to find the tension on the cord here, because there's tension pulling this mass forward and pulling this mass backwards, if we want to find out what that force of tension is, then we have to isolate the 3 kilogram mass. So this is for the 5 kilogram system. And then this is just for the 3 kilogram mass. So the net force equation for this 3 kilogram mass says that the net unbalanced force will equal the mass times the acceleration. Well, now we're dealing with the 3 kilogram object. We know it's going to accelerate at 4 meters per second squared because the whole system accelerates at the same rate. And then what is the unbalanced force on this mass? Well, we know there's a normal force and a weight, but those just balance each other because it's not moving that way. So the unbalanced force is the tension. So this net force equation enables us to conclude that the tension has to be 12 newtons. Now, we had isolated this mass to draw that conclusion. What if we'd isolated the other mass? Let's just check for consistency. So we just said that there had to be 12 newtons of tension there. The string is going to pull this mass backwards with 12 newtons of force as well. So if we consider the forces acting on this mass, then we know there's 20 newtons pulling it forwards and 12 newtons pulling it backwards. So is that consistent with an acceleration? So the acceleration for this system should be 4 meters per second squared. So the net force on the 2 kilogram object, so 2 kilograms, its net force is 20 newtons forwards minus 12 newtons backwards. That's 8 newtons of net force. And if we consider MA, 2 kilograms times 4 meters per second squared, that's also 8 newtons. So that's consistent. Okay, the 12 newtons is indeed the correct tension. So here's another one we can do by the system approach. Now instead of 2 masses, there's 3, but it's the same way. Now we've got a 10 kilogram system. And the forces that are acting on it, it's still frictionless. There'll be an upwards normal force, a downwards weight that cancel each other out. So the net force on the system is just that. Okay, so the net unbalanced force is 20 newtons. The mass of the system is 10 kilograms. So we can divide there and solve for the acceleration of the system. It'll be 2 meters per second squared. Now to find the tension, we argue that this string is pulling forwards on this 3 kilogram mass. The other forces are normal force and gravities, and they're balanced. So the unbalanced net force on this mass is just the tension. It's a 3 kilogram mass, and it's accelerating at 2 meters per second squared with the rest of the system. So there should be 6 newtons of tension in this cord. To figure out the tension in this cord, I notice that that cord is pulling these two forward. So we better use the subscript here. We better call this tension 1. And then we'll call this string tension 2. So I'll call this a 5 kilogram subsystem. And when I apply Newton's second law to that, net force is MA. The unbalanced force on that subsystem is the tension in the second cord. It's 5 kilograms, and the whole thing is still accelerating at 2 meters per second squared. So that must be 10 newtons of force. Again, we'll check for consistency. So we found an acceleration here of 2 meters per second squared. So there should be 6 newtons of unbalanced force on that mass. If there's 6 newtons backwards there, and what did we just find? 10 newtons here, that gives a net force of 10 minus 6, and that equals ma. So that's consistent. On the 5 kilogram mass, 20 minus 10 would be 10 newtons of unbalanced force, and again that equals ma. So that's a consistent solution. So there's 6 newtons of tension in this string and 10 in this one. Okay, so here's another problem. Now, this system is 2 masses connected over a pulley, and what accelerates the system is the weight of this hanging mass, the weight of the 4 kilograms. Now, the weight of 4 kilograms is 4 Gs, or 4 times 9.8, is 39.2 newtons of unbalanced force. So that is the net force on the system. So this is a 6 kilogram system because these 2 masses move together with 39.2 newtons of unbalanced force. So we can solve for the acceleration by division. That's 6.54, I think, meters per second squared. 32 goes in 5, 20 goes in 3, yeah, 6.53. And so that's the rate at which the system will accelerate. And now, again, to solve for the tension, I just isolate one of the masses, and I know, say, that this first mass here must be accelerating at that rate. The only forces on it are normal force and friction, and then there's tension here in the cord. Okay, so applying Newton's second law to the 2 kilogram mass, the net force will be ma. The net unbalanced force is the tension in that cord. It's 2 kilograms accelerating at 6.53 meters per second squared. So what is that? That's 13.1 newtons of tension. Now, if you want to check for consistency, you can see that if this mass accelerating at 6.53 and 39.2 newtons of downwards weight, is that consistent? Yes, because the mass of 4 times the acceleration of 6.53, that's about 26 newtons, and the downwards weight minus the upwards tension also gives you 26 newtons. So that's consistent. Now, what happens then if friction is non-zero? Well, if we look at the problems that we've done, you can still find the net force on the system. Right? The net force on this system, if we view it as a system, will be this applied force, and then you'll have to subtract the 2 frictions. So it's the applied force minus the friction on the first block minus the friction on the second block. That's the net force on this system. Over here in this problem, earlier we said the net force was just the weight of the hanging mass, mass 2 times g, and there's no friction on this one because it's in the air, but this one sliding along the surface will have a friction force. So here, for this problem, we can again write in a word equation. The system net force is the weight of m2 minus the friction on the first mass. But there's some accounting difficulties that start to present themselves, and so we'll actually end up solving this one in a slightly different way. Instead of treating the 2 objects combined as a single object, we're actually going to consider them separately. So how will that work? Well, here we have a problem with friction. We're applying a force to the system. So we're going to draw forces for each of the masses individually. Now we know they're connected together, but we're going to treat them as if they are 2 separate entities that are accelerating at the same rate. So here are the forces acting on the 5 kilogram. There's a normal force and a weight. They just cancel each other out in the vertical direction. Then we've got a force of friction. I'll call that friction 1 for the first mass. And we've got tension pulling the mass forwards. So first we can find this force of friction. It's mu times the normal force. And in this case, as we said, the normal force is the same as the weight because it's not moving up or down. So the mu constant for the surfaces is given as 0.15, and this will be 5 times 9.8. So that is how much friction? Okay, so that's 7.35 newtons of friction. There's also friction on this block, and that works out to 4.41 newtons of friction. That's friction 2. There's also tension pulling this block back. And then there's this applied force here of 20 newtons pulling it forwards. So we're going to write net force equations for each of those blocks. First of all, for the 5 kilogram object. So these objects are going to accelerate to the right. So the net force must be to the right. That tells us the tension exceeds friction. That tells us that the net force is the tension minus that first force of friction. Okay, so tension minus friction, that's got to equal mass times acceleration. This is for the 5 kilogram object, so the mass is 5. So net force equals ma. So this is an abstract net force equation. It's got 2 unknowns in it. So by itself, it's not enough for us to finish the problem. But if we consider the net force on the other object, then if we put these 2 equations together, we will be able to solve it. So what is the net force on this mass? Well, again, it accelerates to the right. So the force to the right, it must be the larger one. So that's this applied force of 20 newtons. And then, I'm just not putting units in here just to make it easier. Then we subtract the forces to the left, which is tension. Tension acts to the left, so we subtract that. And then this second force of friction of 4.41 newtons, which I forgot to write in. That also gets subtracted. That's also acting to the left. So that's an expression for the net force on the 3 kilogram object. That's got to equal the mass times the acceleration. Okay, so we're going to solve these equations simultaneously, and that will tell us what the acceleration is for our system. So an easy way to solve these is just by adding the right sides and adding the left sides. If we add 5a and 3a, we get 8a. When we add on this side, we've got plus t and minus t. That's just going to cancel out. And then what we're left with is 20 minus 7.35 minus 4.41, which is the applied force minus the 2 forces of friction. And this number 8 here is actually the mass of the system, the combined mass of the system. And if you look back to the previous slide, that's exactly what we said we would do. To find the net force on the system, it would be this applied force minus the 2 frictions. So we've arrived at quite a sensible result. But okay, so now to solve for the acceleration, we simply subtract these and divide by 8. And so we get a little bit more than 1 for the acceleration. And then to find the tension, you could resubstitute into either of those equations. I'll substitute into the first one. And we should get 2.2 newtons of tension. If you substituted the acceleration into the second equation, you should get exactly the same result. Okay, so this is the second approach. This is called the free body approach, when you consider the 2 objects as being separate objects with the same acceleration. And ultimately, this will be a more successful approach as the problem gets more complicated. So when we meet together, we will do exactly that. We will do a more complicated problem using the free body approach. Now we've got 3 objects here and an overhanging pulley. And then we'll consider some applications, such as this system, which is known as an Atwood machine. So more on that when we meet together in class.